As we move forward into looking at electric circuits more, it'll be helpful to go over how diagrams for how to build circuits are drawn. And the idea with a lot of this is it's mostly just a pictorial language, and a lot of the symbols, even though they look mysterious, are based on what those devices at least used to look like back in the day, even if they don't look like it now. So I'll start by going with the battery. We've already seen this. So the way I've been drawing a battery so far is, say, like this, or you'll see it drawn on its side like this. And this is true for a lot of, for every symbol. You can either draw it vertical or horizontal, but when you do it, you have to rotate the entire symbol. In any event, the long dash here corresponds to the positive terminal of the battery, and the short dash here corresponds to the negative terminal. And I always just kind of remember that by thinking that the short dash looks like a minus sign. Now, if you look at diagrams in other places, you'll see that there will be sometimes quite a few of these long and short dashes. In many places, you'll see them, for instance, draw it like this, and that amounts to the same thing. Now, you might be wondering, how the heck does this even look like a battery? And you have to go back all the way to the very first voltaic pile, it was called, made by Alessandro Volta himself, the person for whom the volt was named. He's also the person who made the frog's leg twitch, showing that nerve signals were electrical impulses. Anyway, an older convention recognized that for virtually every chemistry of battery at the time, each cell in a voltaic pile added 1.5 volts to the battery. So back in the day, if you just drew this would be 1.5 volts, and then say this would be 3 volts here. And if you're doing your car battery, well, hold on to your hat. This is going to take a bit. 1, 2, 3, 4, 5, 6, 7, 8. So that would be a 12 volt battery, just to get absolutely ridiculous. But if you go and look at old schematics of cars and such, you will see this actually being used. Now, it turns out that with rechargeable batteries, the rule of thumb that you can get 1.5 volts per cell within a battery really doesn't hold anymore, and the values are all over the map. So what's normal now is to just draw this or this and just write the voltage next to it, say 12 volts, or maybe this was 6 volts, whatever. You just write whatever the voltage is next to it. These two are going to be the most common. The reason that some people choose to still draw this is just to make it harder to confuse a battery with a capacitor. So in fact, let's go ahead and just revisit the symbol for a capacitor. And that is 2 parallel lines like this. And this is meant to remind you of the parallel plates of a parallel plate capacitor. Even though the actual physical device usually looks like a blue cylinder or else a sort of a brown circle-ish blobby thing, are the two most typical package designs. Again, this is like some of the very first capacitors we're talking about, so it'd be a parallel plate capacitor. This also helps to explain the symbol for a resistor. It's just a bunch of jaggies. And this is because the earliest resistors that were made were actually made using the kind of wire, nichrome wire for instance, that you would use in your toaster, and you would wind it up pretty much the same way that they do even today in a toaster. Or if you can find like one of those old-timey space heaters up in your grandma's attic somewhere, the ones that were built before anyone cared whether the things would burn the house down or whatever, you'll see the wire in the heating element run back and forth in a zigzag. And so indeed, this is the symbol for resistors. It's just thinking about that high resistance wire being zigzagged back and forth. Now, you should be very careful here to draw with jaggies because there is a symbol for another device that we will encounter later called an inductor. And I will draw it now, that uses loopies like this. And this is because it's literally a coil of wire. And so that's what that's representing, is a coil of wire. So make sure to keep your jaggies and your loopies distinct. Don't draw a resistor as loopies, because then people will look at that and think you're drawing an inductor. Continuing on this vein here, I'll go ahead and also introduce a light bulb. The symbol for a light bulb is basically just you make a little circle like this with a little circle around it. And what this circle is the filament of the light bulb. And again, this is getting to the fact that if you look really carefully at those, you'll see that they're actually coiled up. That was to provide a bit of springiness to deal with a magnetic effect that happens that attempts to change the shape of the filament when you first run current through it. So in order for them to live longer, they get coiled up. And so that's, again, just trying to remind you of that. There is no actual connection inside the light bulb like this. It's just how people draw it. Now, if you are drawing this vertically, and the circle here represents literally the bulb of glass around the old-timey light bulb. If you draw this vertically, you have to rotate the entire symbol. So if you're drawing it vertically, you would do it like this. Definitely do not do this. That is just bad. Because then what you're telling someone to do is attach wires to the glass, and that's probably not going to work so well. Okay, switches. Let's do a switch. So the symbol for a switch, whoops. There we go. So the symbol for a switch looks like this. And it is a little arrowhead, like so, and you got a couple of dots. And the idea is, if you look at like those old Frankenstein movies with the giant knife switches, this is sort of like the insulated handle, the knife switch, but somehow it morphed into an arrow. Yeah, I don't understand that either, but that's what happened. And so you should be thinking of like literally closing the knife switch. And so these are the contacts on the one part of the knife switch. This is the contact on the other side of the knife switch. So if this were closed, it would connect through. As drawn, this is open. Now, this is just a typical on-off switch. Switches come in a baffling array of diagrams, depending on how complicated your switching gets. I will just do one example for now, and if we need anything else later, I'll introduce it at that time. This is an example of what is called a single pull, double throw switch. So the pull is this bit here that can flip back and forth. The throw is the number of places it can land. So this is a single pull, single throw switch. It can only be thrown to one place. Here it can be thrown to two places. And yes, this terminology is actually coming from railroad switches, which move railroad cars around between tracks. The language got commandeered into electricity. So you go ahead and with something like this, you can decide that either the current will flow like this, or you could go to the other throw and energize a different part of the circuit. And there are many more designs than that, but this will be enough to get us going for now. So then what we're left with is that we need to just somehow hook it up. And casually, people will say that the symbol for a wire is just a line. But I'm going to put that in quotation marks because it turns out that technically this is any negligible resistance connection. So for instance, a typical chunk of wire in a typical device might be on the order of 1/10 of an ohm. Compared to other things in the circuit, that's usually pretty negligible. However, this symbol for a wire could just mean that you literally physically connect the two things together. So for instance, you could just, if you were, say, attaching a resistor and a capacitor together like this. So I have a resistor and a capacitor, like so. What you might actually end up doing physically, one possibility would be you take your resistor, which they basically just look like cylinders with colored stripes on them. And you might actually, and there's like a wire chunks hanging out of both ends. And you might actually physically drop in a drop of solder to attach it to your capacitor, which will look usually like, again, some sort of a cylinder, and I'm making a real hash of that. So let's try that again. There. So that's one way you could do it, say with a drop of solder. Or you could have chosen to instead do this. You could have used a wire nut like you see in home wiring. Or you could have decided to twist these together. So you might see if you just tell a technician to do it, one way they might decide to do it would be, say, maybe like this, or they bent this down, and then they actually just kind of physically twisted the capacitor in. Like that. That would count. Or you could have had a chunk of solder, a wire, another chunk of solder. These are all possible. So if you just draw a diagram and you don't leave any instructions, you are leaving that to the discretion of the technician how exactly to do it. In fact, one perfectly valid way to do it is that a lot of things are in metal chassis, and it's very common to use to hook up the negative terminal of a battery to that negative chassis, and then anything that needs to home run back to the battery, you just attach to the chassis wherever it's convenient. So these are all things that do get done. Alrighty. So the other thing that I want to get into here, and then in the next video we will start tackling using Kirchhoff's laws to look at circuits, is I want to bring in the assumptions of an ideal circuit. So I will start with the most reasonable assumption and work my way to the least reasonable. So this will be the most reasonable. And this will be the least reasonable assumption. So the most reasonable assumption is that all wires are ideal. So this means that we will say that the resistance of the wire is 0. And by twinkle, twinkle, little star, delta V equals I times R, this means that the voltage drop across any wire is 0. Now, this is about as reasonable as it comes because there are a class of materials called superconductors that if you make them ridiculously cold, quantum mechanical weirdness does occur to actually legit make the resistance exactly 0. So this can actually be done at least in a lab. In practice, your typical interconnection wires are on the order of 1/10 of an ohm or so. Your devices are probably on the order of at least 100 ohms or something like that. And that's, close enough to 0 that it's not a big deal. Especially in light of the less reasonable assumptions coming. Now, this ideal can break down, and something that we will get into when we look at AC circuits is if you are running your wires over very long runs. So for instance, like power transmission lines, stuff like that, which are hundreds of kilometers and even in a few cases over 1,000 kilometers long. That's an awful lot of wire, and even if you make that wire really fat, and they do, the resistance is definitely not 0, and that is something that you do have to worry about at that point. But we will cross that bridge when we talk about AC circuits later on. Okay, so we're already getting to now a much dodgier assumption, and that is that all resistors are ohmic. So under this assumption, this means that we can treat the resistance as a constant, and that means that Ohm's model applies. And I like saying Ohm's model versus Ohm's law because Ohm's model is basically saying, well, if the resistance is a constant, then we can treat it like it's a constant, which is kind of circular. So I'm not a fan of calling it a law. You're just modeling the resistance of a device and saying that at least in a certain region, what we call the ohmic region of the device, we can approximate the resistance as a constant. Well, here's the thing. Even if you buy really high-grade resistors that are manufactured incredibly well, even basic bench equipment, like the sort of thing that you can get from the local big box store, will be able to show up as you run a range of currents. You will see that the device is nonlinear, that the VI curve is indeed a cubic, and that shows up within the resolution of just even basic voltmeters and ammeters that you can pick up at your local big box, building supply store. So this assumption that resistors are ohmic is not a terribly good one. The way the manufacturers kind of cheat on that a bit is when you look at how the color codes for resistors work. And it's just they paint colors onto the resistor, and the colors stand for numbers. The kind of colors used they use special heat resistant paint so that you can still read the value later, even if the device has been used for a very long time and you might otherwise burn off markings. And by the way, be very careful looking up the color codes. There is one widely used mnemonic out there that is incredibly offensive to just about every identifiable group of people you can imagine. And I'm not trying to nag people into looking at it. It's like, no, really, it's fairly gross. Go look at places that are more education aimed, where they will give you better mnemonics than the ones that they came up with back in, say, the 1940s and 50s. Anyway, in this system, the last color that gets painted on indicates the tolerance of the resistor. In other words, to within how many percent is the resistor going to be its stated value. If there is no band, it's 20%. If they do paint bands on, it corresponds to 10 or 5%. There are some extensions to do a little better, but to this code to do a little better than that. But seriously, a gold band, a gold tolerance band, means that you are paying for one that is as good as 5%. Well, these devices are definitely ohmic to within 5%. So basically just them saying, yeah, okay, we'll just give you a really big percentage and then we can pretend it's linear even though it's not, is basically how this game gets played. So it's not ohmic, but unless you're doing incredibly hyper-precise things, it's usually good enough for what you need to do. So, but if you are being careful, you may actually have to look at the VI curves for the device. And then finally, the least reasonable of all the assumptions is that the batteries are ideal. So here, this means that the internal resistance of the battery is 0. And this is a completely bogus assumption. Because you have ions transporting within the battery to move your charge around, those ions are colliding with other molecules in the battery chemistry. I mean, that there's plenty of resistance in a battery. I mean, it's not off the charts high. It's lower than probably the devices you're hooking up, but it's certainly not at the level where you can just totally drop it down to 0. And the fact that the batteries have internal resistance is why, if you've been operating a battery-powered device for a while, you might notice that the battery starts feeling toasty. In fact, this is actually a serious concern for rechargeable batteries, especially in high-stress situations like electric vehicles. In electric vehicle batteries, the manufacturers go to great lengths to create heating and cooling systems for the batteries so that they are always operating in a Goldilocks range of temperatures. If they're way too cold, undesirable chemical reactions can occur that shorten the life of the battery. But again, same deal if they get too hot. So, if someone is just really stomping on it, driving at, high track speeds or something like that, if, if cooling measures are not taken, it can really shorten up the lifespan of the battery. This is, in fact, an issue that some manufacturers did discover in early on, but at this point, everyone has learned their lesson, and they go to the effort of liquid cooling their batteries so that if it gets too hot, they can stay within desirable temperatures from a chemical point of view. So, you have to worry about the internal resistance of the battery. However, it turns out, and we will see this in the next video when we estimate the internal resistance of a couple of D-cell batteries, that you can model the internal resist in a real world battery as an ideal battery attached directly in series with a resistor that models its internal resistance. And so because you can do it, you can so accurately model it, it's okay to model the battery as ideal. And then if you need to worry about the internal resistance, you just add on this virtual extra resistor and everything gets modeled just fine. So in the next video, we will recap Kirchhoff's node and loop laws and use that to start analyzing electric circuits, finishing up indeed with estimating the internal resistance of a pair of D-cell batteries. So catch you in the next video.